Hello everyone and welcome to my Yamaha CS20m and Yamaha CS40m restoration videos. I'm planning to do a couple of videos and I've wanted to get these two on the bench together for ages because it's a really good comparison. A lot of people think that the 40m is just a two-voice version of the 20m and it's not really true. The 40m has a lot more features and the ranges of sound that it can do are a lot greater than the 20m. They both have a very similar sound, that typical CS Yamaha sound. One of my favourite sounds ever. I love the filter so much. So it'll be really great to get another one up and running instead of going in the bin. So I'll just compare them a little bit now. I won't go into the sound. I might even do that on a separate video. I might even do a shootout later on. But for now, I'll just explain basic functions and then we'll get to repairing the CS20. So, firstly, I think we'll start with the 20. We've got two basic VCOs here. You'll notice the white knobs and the yellowish knobs or orange knobs. The reason for the different colors is that when you save a patch, the white knobs aren't saved with the patch. So when we look at the schematics and the electronics inside the instrument, these white knobs will go straight to the analog voicing boards, whereas all the cream, orange, yellow, whatever you call them, all the other colored knobs will go through the processor so that they can get saved. So it's the same on the 40M, but you'll notice there's less white knobs, so more parameters can be saved, particularly the pulse width modulation can be saved here, whereas if you notice on the 20M, it's a white knob. So there's a lot of other differences too. This glide circuit's like just a release time really, with the VCO CV, whereas on the 40M, you've got another envelope generator. And that, with this envelope generator, you can actually do a lot more stuff too. The LFO has a lot more parameters. On the 40M, we can see that there's just a rate really and a repeat switch on the 20M. So on the 40M, you've got speed and you've got the depth, so you can affect it with this envelope generator. And it's also got a ring modulator as well that the 20M doesn't have. And this has its own VCO that can be modulated by this attack and release generator as well. So there's a lot more, and also you can affect the pulse width with more sources, including this attack and release generator. So there's a lot more there. There's twice as many memories. You've got unison as well, and you've got two different types of sustain as well. And the VCA's section's more complicated. You can add a sine wave in from each of the two oscillators. So you've got, see these two sine waves, 1 and 2. You can add in at the last phase. Whereas here on the CS20M, you've only got one. And I think that tracks VCO1. So you're missing the ability to add a sine wave for VCO2. So there's a few things. And also the output, you can switch it to permanently on, which is cool. And also the keyboard's bigger. And two voices, of course, in unison. So both wonderful synths. The 40M's much more powerful, but wow, you'd be happy with either one. So let's start with the repair. And why don't we start with finding out what they're supposed to sound like. So this is the CS40M. And this is the CS20M. Okay, so so there's no sound. Well, there is some sound. I'll show you in a second. But there is a really big clue about what's going on, and that is these 4 LEDs here above the 3 red buttons. Now, I don't think anyone would try and load, store, and write at the same time. And if I was the CPU and I was being told to load, store, and write all at the same time, I'd get confused as well. My guess is that there's probably some multiplexing and demultiplexing issues on this synth, and that's confusing the CPU, or at least that's the best scenario. The worst scenario is that we don't have any of those problems and the CPU is dead, but hopefully not. We'll see how we go. So let's have a listen. If we turn the output up, we get this weird gating of the VCA that matches the LFO speed, but nothing else works. Oh, a couple of little things might maybe work, I don't know. No. Oh, that's bad. Noise works. Oh, okay. So that's pretty wrong. So we've got a lot of work to do on the repair. So let's open them up and have a look. Okay, so I've turned them off and I've unplugged the power cable. Now to have a look inside, the top panel just lifts up like most synths do. It's got a big long hinge that goes all the way along the back. So to get that open, there's 2 screws on each side that come up from underneath, and there's 1 screw right in the middle underneath. So don't forget the one in the middle. And it's the same on the 40M. There's 2 screws from underneath, and there's 1 in the middle, 2 screws on the other side. So I've already gone and taken out the screws, so we can lift the top panel straight up. And I've left this in to show you some really kind person has tied a piece of rope or string here to make sure that the top panel doesn't fall all the way back. That's very nice of them, but all they had to do was look on the side, and there's actually one that's built in. So if you have a look here, this flicks up and it hooks onto this point here, like this. There you go. That's how it's supposed to happen. So I can cut this off now. So it's the same with the 20M. Just lifts up. And then we put on the specially made hook. There you go. So that's the CS20M. And that's the CS40M. So you can see it's significantly bigger. The boards are all bigger. So it's not just a matter of there's an extra voice card. All the boards have been redesigned, and I think that's because of all the extra modulation options. So first I'm going to talk about the layout of the CS20M, and then we'll go and do the same thing in the CS40M. So I'm going to get some more light first. So firstly, on the top panel, we've got the 2 main panel boards, a switchboard and the input and output jack board. There's another board on the back that I'm going to talk about a bit later. But first, let's have a look at the 4 that are on the bottom. So firstly, this one, PGM board that has the main processor on it, some demultiplexers and all that kind of stuff, switching chips, and the 2 memory chips. So this controls the patch memory and accessing the RAM to pull the patch memories out, and all that kind of stuff. Also probably the save and load for the tape interface, because that is concerned with the RAM chips. So this is the board we'll have to probably look at the most in the CS20, because that's where all our problems are with those LEDs with the save and write buttons on the panel that were stuck on. So a lot of our problems will be on this board. Now underneath it we have the DM board. Now if you've watched my AX60 video, the first video in the AX60 restoration series, you'll probably recognize this circuit. So if you have a look here, there's some, hang on, I'll just focus the camera. There's some op amps, and there's a whole lot of capacitors, and here we've got some multiplexers. Now, even just by looking at that board, all the rows of capacitors next to op amps, I already know what that board is. So this must be a sample and hold board for distribution of the control voltages from the CPU. So we've got our multiplexers on this side, which are the switches that let in the voltages, the capacitors that store the voltages, and the op amps that read those voltages and then output to the analog voicing circuits. So we won't have to touch this board, at least not yet anyway, because we don't know if we've got any problems with it until we actually start to make sound. That's a little while off, that board. So this top board, this is the analog voicing circuit, or at least part of it. In fact, this whole board is probably the equivalent of one of those voicing chips in the Junos, because it has the VCF and the VCA and the envelope generators on it actually as well. Now, it's missing the oscillators. So, well, where are the oscillators? Well, that's on that little board on the back of the instrument. And the reason why the oscillators are here is so that you can get access to the back panel to do the tuning. So the oscillators have been separated from all the other analog circuits and put on the back panel. Okay, so that's the voicing board. And then underneath here, we have modulation. So there's a whole lot of switches, basically off-on switches and routing options, and then a whole lot of the circuits that actually do the modulating. So that's it for the layout of the CS20M. So let's have a look at the CS40. Okay, so we have again the 4 boards, but they're all in a different order this time. So up here we've actually got our analog voicing board with the 2 voices of the VCFs, VCAs and the envelope generators on that board. Now on the back panel you can also see a much larger VCO board, because there needs to be twice the space now because there's 2 voices. Now underneath this board, look at that, the rows of capacitors again. Look, 2 huge rows and a whole lot of op amps next to them. So that board must be our control voltage sample and hold circuit board. Now on the top here, what is this one? Modulation board. So that's the same as CS20, except it's a lot bigger now. Lots more stuff happening, lots more chips, because there's lots more to do on the CS40. Then underneath, hiding, is our main processor and our RAM and all that kind of stuff. So this board is actually fine in the CS40. We can save and load patches and all that kind of stuff. So there's really not much differences in the panel boards, besides the panel boards are bigger and the output boards are bigger. So that's it, really. So let's focus on getting this board to work. Okay, so the power's on, and the first thing I've done is check the power supply, and I've used this connector and this connector. So you can see printed on the circuit board, it has all the voltages written there, so plus 15, minus 15, and on this one we've got plus 5, minus 10. So all I've done is put my probe in the top of those plugs and check for the voltages, and they're all present, which is good. So the next thing we need to do, especially if we're troubleshooting CPU problems, is check that there's a clock that's driving the CPU, because without the clock, it's not going to work. It's going to look dead. So this test involves this connector here. If you have a look on the circuit board, there's a little symbol. It's like a 0 with a line through it. So we're using that pin with our probe, it's just on 1-to-1, and I'm using ground. You don't really need to use ground with clock signals like this because you'll still get a square wave on the oscilloscope, but I'm using it anyway. And the spec for this one is 100 kilohertz, plus or minus 0.5 kilohertz. So if we have a look on the oscilloscope, we're indeed getting a square wave, which means our oscillator for the CPU is working. And this scale is 2 microseconds per division. So 2, 4, 6, 8, 10. It's got 10 microseconds total, which is 100 kilohertz. So we're in spec, which means our CPU should be doing stuff because it has a clock signal that works. Now, the most important logic signal that we have going to the CPU is the reset signal. So when we power up, we do a quick reset pulse, which starts everything off, and then we must hold that low or else the CPU can't function because it'll be permanently in reset. So this is a very important test to do, and this one is done on IC10. So it's this IC here, and it's pin 10 of IC10. So this is a 14 pin chip, so we've got 7, 8, 9, 10, so it's third from the top on the left hand side. And I'm going to use my probe again. I'm going to have to hold it there with my hand, and we will need ground this time because we're testing real analog voltages. So what we need to see is, well, when the power's off, we'll just see ground because that's what the oscilloscope naturally sits at. But then when we turn it on, we'll see a +5 for about 100 microseconds. Then the CPU will reset, and then that needs to be held low at -10, which is our negative logic level. So what I'll do is set up the camera in front of the oscilloscope so that I can have my hands free to do the test. Okay, so I'm holding my probe on pin 10 of IC10. We're starting at ground, and if everything's working, we should see this line jump up 1 division to +5, and then very quickly, in about 1/10 of a second, jump down to -10, which is 2 divisions, and it should stay there. And if it stays there, then our CPU will be free to process signals. So let's see, I'm going to turn it on now. Yep, and you see it jump, it went straight up and then down very quickly, and it's being held at -10, so it should be good. So what's next? If we've got a clock and we've got a reset signal and we assume our CPU is working, which it probably is, then we've got to check all the logic that controls the signals to the CPU. So there's a whole lot of chips around here which do various functions like scanning the switches and pots on the front board. So some of them are probably faulty, and that does make sense because a lot of them are quite cheap, mass-produced chips, and they're known to fail. There's also some hints on this board too. When you have a look down here, there's some burn marks around that comparator. And there's also a newer chip here, which is a CMOS chip, which is different to the other chips on the board. So I know someone's already tried to replace that. Now, I've had a look at the circuit that scans those switches on the front panel that have the patches and the load and the write and all that kind of stuff. And it's quite complicated how they work. It's kind of to do with timing and the CPU counts, the differences between some logic signals, and then determines which switch is on, and then it's all clocked in as an 8-bit word, and it's all a bit, you know, overly dramatic. So what I'm going to do is rebuild the board and focus on the chips that are in that circuit. Now, I've already tested some of that logic because the hardware manual and service manual are quite good. They give you the test points and they say switch this switch on the board and have a look for that pulse, and none of that's there. None of it's working. So I'm going to have to replace all those logic chips that are in that circuit. So I'm going to go ahead and do that. In fact, I'll do more than that because a lot of these chips are very cheap, like $1 or $2 each. So, I mean, this is a $1,000 synthesizer, so, you know, I'm not going to skimp on a couple of chips and you know, try and save money when most of them are $1. So I'm just going to replace them. Right, so the boards come out of the instrument, and I have already removed all of the non-Yamaha chips. So there's plenty of them, and I've labelled the type on the top of the board. So it's important that after you remove them, that you're left with holes that go right through the board. So make sure that there's no solder left over the holes, because when you put the chip beds in, there's a risk that you might push off the tracks from the other side. So I'm going to go ahead and put in all the chip beds now and the new chips, and then we'll pop the board back in the instrument and have a look. Okay, so the board's back in the instrument with the new chips in. You can see them, they're raised a bit now because they're all on chip beds. And I put in one screw just for good luck. Always helps. And then, okay, so from our memory, these 4 LEDs were on before, like I was trying to write, store and load all at the same time, which is probably confusing the CPU. So let's turn it all on and see if we get the same result. Oh, where's the on switch? Hang on, behind the back. Okay, we're back on. Oh, we got some sound. Let's have a look. So, yes, the LEDs aren't on. And we have a panel light. Oh, that's so cool. So we're basically operational now with the patches, I suspect. Yes. That's good. I don't want to press these because I don't want to load or store or write right now. We will test the sound though. We wouldn't have affected the sound circuits as expected. But hopefully now we pull a whole lot of random sounds out of the RAM when we press these patches. So we should hear something change. Yep. Excellent. So that tells us a lot. Actually, that's really important. So what we've learnt is this. Our CPU is working. All the logic signals going to the CPU are good. CPU knows what to do. It can pull sounds from the RAM. The RAM is okay because every time we press a patch, we get a new different sound from the RAM. So it's not just the same old garbled thing, it's actually different. So we're pulling different sounds from the RAM. Then this is going off to the voicing section, and then it's all becoming a little bit messy. So we've probably got some of these switching ICs bad on the voices as well. But I think we're finished with this board. So that's really good. So we're going to move on to fixing the voice problems. So I'm going to focus now on these 4016 chips because they are notorious for failing, and we have had probably quite a few failures on this board, probably from an old capacitor or a chip that's blown up and then it's taken out the rest of them. So I expect the same kind of damage on the other boards. So I'm going to replace any of those chips now that I think may have been affected, and we will start to fix a lot of the sound problems now too. So I've pulled out the FA board, which I think stands for filter and amplifier, and the mod board, which is obviously modulation, and they sit in the instrument like this, sort of like that, on top of each other, in that spot there. And they've all got a lot of chips on them that notoriously fail. As I said, 4016s, which are just like off-on switches really. And there's a whole lot of them on the mod board too. We've got some quad comparators which might be okay. I might leave them in first, see how far I get, and some other logic. So if I pull those chips out, put in chip beds and then new replacements just like I did with the CPU, hopefully more of those problems get fixed. And in the meantime, I found something else that's really interesting. Look at this connector. It's wobbly. In fact, I can tell you it's not even connected underneath. I can definitely see it wobbling here. There you go. Look at that. So that entire connector is probably not even physically connected into the circuit. So we've got big problems here. So if I just run my soldering iron along those solder joints, we should see another improvement in the instrument as well. Okay, so we've replaced all the non-Yamaha chips, so all the cheap stuff you can get from your local electronics shop, like the 4016s and the XOR gates, and a few comparators there too. So everything's been done, pretty much rebuilt. I guess it's what you would call a shotgun approach. We've done a whole lot of stuff at once without really concentrating or thinking about it. I think it's a good approach because a lot of those chips are prone to failure anyway, so it's a good idea to replace them, even if it's just to future-proof the synth. And hopefully along the way we've solved some of the problems too. I usually don't start troubleshooting with the schematics until I've done that, because you'll find you get rid of quite a few problems without having to do much thinking. So let's turn it on and see how far we've got, if anywhere. Yes, we got some keys. All right, so the keyboard works. Yes, but it only works while the LFO's on. Right, that tells me something. So we turn the LFO speed up. Yes. So what's happening here is we're getting the VCA gating with the LFO speed. Now that is an option under here, modulation depth. So if we turned this up and put the function on sine wave, that's exactly the sound we would get. But the problem is when we turn the depth down and say put this on square, we still get the full loudness of the sine wave. So none of these switches are working. And it sounds to me like this is stuck on full and this one's stuck on full, because we shouldn't be getting any sine wave at all. So we can prove that by turning the mixer down, and now we shouldn't be getting anything at all, but we're still getting it. It's definitely a sine wave. So if I turn these other ones up, I can hear a little bit of the VCOs coming through, but we're not getting any filter effect either. So a lot of these knobs aren't working. So why did we get the keyboard fixed? Well, it was because we replaced some logic chips, but it wasn't on any of these boards. It was actually on a board that I've forgotten to show you. And the reason why I've forgotten to show you is because it's hard to find. It's the keyboard scanner board. And believe it or not, it's in a really obvious position underneath the keyboard. So you'll need to undo the screws from underneath, and then the keyboard lifts up from the front. Like that, and there it is. You know, if I did this video again from the start and explained where all the boards were in the synth, I would still forget this board. In fact, I've done these synths for a while now, and I honestly still forget it there. So in some synthesizers, the keyboard scanner is actually part of the main CPU, but on this one it's not. It's a separate board. So when I did all the logic chip replacements on these boards, I included this board as well, because there were two rather cheap logic chips on this board. And the one that was faulty was the 4050. So once I replaced this one, the output from the keyboard scanner board went to the CPU, and we had our keys working. Right, there comes a time in every synth repair where we have to look at the schematics. Well, most synth repairs. So we've finished doing all the general quick and easy stuff like replacing all the logic chips and just hoping for the best. And that's served us quite well, and it usually does. You quite often fix a lot of problems like that. But after that point, if you're still left with issues, it's time to dig a little deeper. So I'm going to do that now. So first I'll explain the signal flow. So when you turn knobs or sliders or press switches on the front panel, all of those voltages are sent to the CPU, and then the CPU reads them, and then it does either two things with them. It either stores them in RAM if you save a patch memory, or it sends them out via this sample and hold board to the voicing circuits, and we make real sound. So I think that our knobs and sliders and all that are probably okay. I know the CPU is okay, and we've replaced all the other logic chips on that board, so I'm not going to look at that board. So I will start troubleshooting from the point where the CPU sends out the instructions to generate those CVs, which happens on this board, from the actual op amps that emit the CVs all the way through the voicing circuits. Now, somewhere in that chain of things we will find the fault. So logically we'll start at the start. So I'm going to look at this board now and measure those CVs coming out of those op amps. Now if they're okay, then we just have to look at the voicing circuits. If they're not okay, we have to fix this board. Now here is the circuit representation or the schematic of our DM board, so this board here. So we've got our 4 multiplexer chips, which in this configuration are working as demultiplexers, but I don't care about the terminology. So they're here, these 4. We've also got these groups here, which are representations of the op amps and the capacitors. So what happens is the CPU sends in some clocking signals really to tell these chips where to put the voltages from the knobs and the sliders. So there's one main clock which is passed down the line through the chips, and there's another one that comes in the side here. The CPU sends voltages one at a time down these lines and fills the capacitors. And the voltages that it puts in here are determined by what it finds are on the front panel. So when you turn a knob here, there will be that knob will correspond to one of these little boxes, which will be 1/2 the op amp. And these demultiplexers will fill that box with that voltage that's from that knob that you're turning. So when you turn that knob to full, you should have the full voltage here, and when you turn the knob to 0, you should see the 0 voltage here. So that should track the knob on the front panel. If it doesn't and it's stuck on full or 0, then we know that one of these parts is faulty, and it's most likely the multiplexer chips. They always fail. So it was the same on the AX60. I had several multiplexer chips fail. So I'm expecting one of these to be bad. But to find out which one it is, we need to test the voltages here and turn some knobs. And so whenever we find the voltage varies with the knob turning, we know that one is okay. So I'm expecting to find at least one of these faulty. And I think it's going to be this one, because our sine wave is always stuck on. And also it's always being modulated, so probably these ones too. So somewhere along here, where these ones are, let's have a look, 21, number 21. So somewhere around here, next to the IC3, I suspect will be faulty. So let's test the voltages now. It's really easy to do. You just put your voltmeter in the plugs here to the number that corresponds in this table. So if I'm going to test the knob that turns up the sine wave that goes into the VCA, we just put our probe in here on number 21. So there, if I just test 21 and ground, I should see the voltage go up and down when I turn that knob on the front panel. So I'll do that now. Okay, so the probe is in 21 and ground, and we're getting 13.3 volts. Now, if I turn that knob here down to 0, we should get 0. And we're not, it's 13. So I'm going to do another one now to show you what should happen when they work. Okay, so now I have my probe in pin 4, and pin 4 is on the table the modulation depth for the first VCO. So I've got near ground now, and if I turn that knob, where are we, modulation depth, to say halfway, got 2 volts. Turn it up a little bit more. Got 10 volts. Right, so that one's working. So our modulation depth number 4 is working. And our number 21 for the VCA is not. It's stuck on full. In fact, it's stuck on more than full. It's way more than 10 volts, it's 13 volts. So I know that this tells me that where our number 21 is, up here, this multiplexer is probably dead. Now it could be these op amps as well, but I've already gone and tested these other ones and I know that they're all faulty. They're all stuck on full. So from 20 to 29, which is here, the filter selection, high pass, band pass, low pass, and all these ones down to 29, the attack time on the VCA, they all don't work. They're all stuck on full. So it has to be this YM617 multiplexer here that's dead. Now, the unfortunate thing, what happens when one of these chips die, is it takes out all the other chips that are down the line, because there's this one main clock signal which is passed from one chip to the next. So if one of these chips dies, that clock doesn't pass to the next one. So in this case, 3 and 4 will both seem dead. So if I swap them around and put the bad one at the end, these should appear to be working now because I bring the good chip up to here. So I'm going to swap IC3 and IC4 on the DM board. Okay, so the two chips, the IC3 and IC4, have now been swapped around. And I'm back to monitoring number 21, which was our VCA sine wave level. And look, we've got 0 now, so it's no longer 13. And if I now move this knob to say halfway, I get 2 volts, yes! And so now if I move it the full way, I get 10 and not 13. That's awesome. So we have this multiplexer working now. So we've got these 3 working, and this one at the end is faulty. So I will need to buy another one of them, and they are super rare, almost impossible to find now, but I think I found one. So once that comes in, I'm going to put it in the circuit. Okay, I got the YM617 chip in, ironically from Japan. Probably came from another CS20 or CS40, because they're the only 2 synths that used that chip. Got the old one over here with black texture written on it saying dead. And I've moved on a bit actually, because now we've got all the control voltages working. We can finally troubleshoot the analog parts of the board, and troubleshooting Yamaha synths is actually really easy. So what you do is you just put the Yamaha chips on chip beds, and they usually come in pairs or more than that. There's quite a few that you can use to switch around and see which one's the dead one and which one's the one that works. So all I've done is switch them around. So up here we've got the wave shapers. So one of them was dead and it was causing VCO2 to not work. So all I did was switch the 2 wave shaper chips around, and then VCO1 didn't work and VCO2 worked, so I knew which one was bad, so I've labelled it as bad. Over here we had the envelope generator for the VCF not working. So that was easy. I just swapped the envelope generator from the VCA, and suddenly I had nothing come out of the VCA, so I knew that that one was dead. So I've marked that one as bad. And the other analog fault we had was that annoying problem you were seeing with the sine wave, always turning the VCA off and on. That's because one of these chips here, these are like voltage controlled amplifier chips, IG00151. And one of them was bad. It was stuck on, so it was always letting that sine wave through. So that was on the mod board. So what I've done is I've gone and ordered those chips. So the wave shaper was IG00158, and the envelope generator was IG00159, and the other one, which I said before, 151. So I've ordered those 3. They were really expensive. Everything in this synth is expensive. And they've come in already. So here they are. You can see here the 158, the 159, and in the middle the 151. And I've got some other expensive chips from another very special synth that I'm super excited about. My favourite synth of all time, actually. I'm about to repair, but I will keep it a secret just a little bit longer. Now, before we put these in, we have a really important job to do, and that is get rid of all these blue capacitors. So the tantalum capacitors, they're what blow up. And on this synth, it was one on this board, I think. Can't remember exactly where it was. There was a blown up mark. I know this comparator blew up, but it was a tantalum cap that blew up initially. I don't know which one it was. So, doesn't matter. All of them have to go, especially the ones that are only rated 16 volts. So you can here see 10 microfarad, 16 volts, anything with 16. It's not as critical to replace the tantalums that are 35 volt rated because they're quite far above the supply rail. So, I mean, the supply rail here is probably 15 volts. So 35, that's enough margin. But these ones over here that are 16, that's really close to 15. So no wonder they blow up after time. So I'm going to replace all of those capacitors first because I don't want to put my lovely new chips in and have another one of these caps blow and take out all the chips that I just bought. So we really need to do the capacitors first. And after that, we put our good chips in and finally we should have a working synth. Awesome, let's do it. Right, so I've got a whole lot of old tantalum caps and some bad chips. And in here, we've got a whole lot of new stuff. With the tantalum capacitors, I usually try and replace them with metal film caps because they're also low leakage. You don't want to do them all with these electrolytic caps because they're not low leakage. So you've got to try and match the properties. So just look on their schematic and just see where the capacitor is used. If it's in the audio path, use metal film, and if it's just a filter cap, then you're okay to use the electrolytics. So I've put my new chips in here and here and underneath. So we're all ready to give it a test. So it's very exciting. Excellent, it works, that's awesome. So, actually, in a matter of fact, I've got some sliders, I think, that aren't working, so I might have one more VCA, one of those IG00151s that aren't working. But most of it now is pretty good. I've also got the sine wave working properly as well, so I can add that. Put on a high pass filter. And some resonance as well. So most of it is working now. The rest I'll finish off after the video because it's gone for half an hour now. So I'd like to limit the videos to about half an hour. So that's awesome. I can't wait to compare it to the 40M. But I may not do that straight away because there's a couple of things that I need to get done first. One of them is my friend's Kawai SX240, this one. It's an awesome synth that I've been waiting to use one for ages, and they're just not around. So I'm quite excited to have a go at that one. It was left in the rain too, so that one's pretty stuffed. And yes, it's my exciting secret synth. Ooh, what is it? I'm so excited, I can't wait for that one. Alright, so that's it for now. Hope you enjoyed it. It was a long one, this one, but we did a lot of stuff, so that's good. So see you in the next video.